Are we good? Okay, we're good. All right, jumping into chapter 7. We're gonna do chapter 7 a little weirdly. There's sort of a math part of chapter 7 and a conceptual part of chapter 7. I don't think 7:45 is the best time to get into the math part of it, so we're gonna do the equation part now, and then we'll do the math part on Monday. So let's look at chemical equations. All right, first thing to note, you've seen these kinds of things before in lab and everywhere else, but a chemical equation is not the same as a chemical reaction. It's a way of writing down what happens during a chemical reaction. And it has some common elements. So let's look at some compounds that we've talked about today and talk about what happens in a chemical equation. So there's the chemical equation. What kind of a process is this describing? Like, what's a way that you could say that in words? Anybody like say that in a sentence? What that means? Yeah, hydrogen's reacting with oxygen to form water, right? Does everybody see that? How that kind of goes together? Let's write that down, because one of the things we want to be able to do from this chapter is do this kind of translation. So read a sentence about a process and write its equation, and then also look at an equation and write its sentence. We can be a little bit more specific about that. We've got these little things in parentheses. Anybody know what those are for? Want to take a guess? Yeah, the state of matter. So this is going to be the state. So that's G is gas, L is liquid, S is solid. And there's one more that we use that's not exactly a state, but it works well. That's AQ, and that stands for aqueous, which means dissolved in water. We'll see that sometimes. So like when you have a solution of some chemical that you're mixing with something else, that's called an aqueous reagent. Some other things that we should know, some terminology and such. Everything on the left side are the reactants. On the right side is called the product. That assumes that the arrow is going from left to right. We will see some reactions where the arrows go both ways, and then we can have reactants or products on both sides depending on how we want to think about it. So if we were to write this in a sentence, we might say something like, hydrogen and oxygen gases combine or react to form water vapor. So we can put the states in there too. And let's think also about the information you would need to go backwards, to go from the sentence to the equation. So for one, you need to know that when we say hydrogen gas, we mean H2 and not just H. If we just wrote H, that would really be a different process. Same thing with oxygen. We need to know about those diatomic gases. We need to know that oxygen gas is O2. And then we need to know the formula for water. In this case, it's water, so hopefully we all know that formula. If it's something more complicated, we can use the name to figure that out. So if we said something like cobalt-3 hydroxide reacts with, I don't know, what's something that cobalt doesn't really, hydroxide doesn't really react with much. So it's a bad example. But something like that, you could put that, you'd have to be able to draw that compound from that name. So does anybody see any problems with this reaction? There's one thing wrong with it, the way it's written right now. Let's draw it out in molecules.
Isn't there only one oxygen?
Yeah, that's exactly the problem. So if we draw this out in molecules, we're saying a molecule of hydrogen reacts with a molecule of oxygen, which we know from what we did before has a double bond, and it forms a molecule of water. That's what we've said there. So you can see the problem here is one oxygen atom, as this is written, has simply vanished. It's disappeared. And that can't happen because matter doesn't just disappear. Law of conservation of matter, you can't create or destroy matter in a chemical reaction. So there's a problem here in that the way it's written looks like an oxygen atom has disappeared. So how do we fix that?
You add 2 more hydrogens, and then you get 4 hydrogens, 2 oxygens, and 2 H2Os.
Right. So we have to actually react them in a different ratio to get them to work. Why can't we just say add another O on this side?
Because oxygen needs 2 hydrogens.
Yeah, that would be a different reaction, right? Like you can do this reaction and you can see that there's no free oxygen atoms going on in here. That's not something that's created as a product here. So that can't work. What about this? Can we just make H2O2 instead of H2O? That's something different too. Does anybody know what that is? There is a molecule that's H2O2. That's hydrogen peroxide. Is that the same thing as water? It's not. Don't drink it. It's good for cleaning stuff, but it's not really for drinking. So definitely a different molecule. So when we change those subscripts, we're actually changing the compound of what's going on. So we can't do that. We can't add extra stuff. We can't change the compound. So what we can do, or what it really is a symptom of, is that these 2 molecules, hydrogen and oxygen, don't react in a 1-to-1 ratio. They react in a different ratio. If we instead react them in a 2-to-1 ratio, then we can make 2 water molecules, and then everything works out. Our sentence still holds. It's still hydrogen and oxygen gas combining to form water vapor, but we're going to combine them in a 2-to-1 ratio and end up with 2 molecules of water vapor at the end. Now all the atoms are accounted for. 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right. It works out. So that's called balancing the chemical equation. And the way that we express that back up in our original thing here is to put a large number in front of the compound to show that there's more than one molecule reacting in this ratio. So by putting 2's in front of the H2 and the H2O, we're saying that these are going to react in a 2-to-1 ratio and then make 2 molecules of water. So for every one molecule of oxygen, we need 2 molecules of hydrogen. We make 2 molecules of water. All right, so you may just be able to see that sometimes in a reaction, that it needs a different ratio. But sometimes reactions are more complicated than that. So let's look at the last thing we're going to do today is a systematic way to figure out how to put those coefficients in the front of our reactants to make sure everything comes into balance. Has anybody done this before? Maybe a long time ago? Yeah. So we're gonna go through it and show you how it's done. Start with this reaction. This is burning methane, which is the major component of natural gas. When it burns, we're going to react with oxygen gas, and that leads to carbon dioxide and water as products. So this will be just our example. So the first thing you want to do when you see a chemical reaction is don't assume that it's properly balanced, or an equation. Don't assume it's properly balanced. Let's check it out and make sure it is. A good way to do that is just to put a little list underneath each side so that we can check out what quantities of different atoms we've got. So we could say this side we've got 1 carbon, 4 hydrogens, and 2 oxygens. This side looks like 1 carbon, 2 hydrogens, and 3 oxygens. Everybody get the same numbers? If you count them up. Remember that whenever there's a subscript, we're going to multiply that through. So CH4 tells us 4 hydrogens. On the right side, there's oxygen in both molecules. So we've got to remember to add up all those atoms, the 2 from the CO2 and the 1 from the H2O. Okay, so now we're going to start balancing by adding these coefficients, these big numbers in front, until we can get things to balance. Now, if we just like randomly pick some numbers, that's not going to go so well. It's going to be hard to do. So what we want to do is pick some atom to start with and set it up so that that one definitely will become balanced. So like we look at carbon. Well, carbon's already balanced, right? We got 1 on the left and 1 on the right, so we can just leave that one alone. But if we go to hydrogen, then that one's not balanced. We've got 4 on the left and 2 on the right. So what can we put for a coefficient to bring those 2 into balance? Two, right? If we put a 2 over here, then since we have 2 water molecules and each one has 2 hydrogens, we have 4 total hydrogen atoms on the right. The next step, really important, whenever you put a coefficient in there, always correct your numbers below, because that's not just affecting hydrogen now, that's affecting oxygen too. So now instead of having 2 hydrogens on the right, we have 4. And instead of 3 oxygens, we have 4. And there is an element of trial and error to this. So if you aren't sure what number to put there, you could try something and see if it works. Look for the quantities, calculate it out, see if they match. If not, try a different number. Okay, so we're getting closer. Carbon's balanced, hydrogen's balanced. So now how do we balance the oxygen? Yeah, we're going to add 2 on the left. So if we put a 2 here, that gets us 4 total oxygens. Right there. And then I think we're good, right? Everything's in balance. So you check your numbers. The nice thing about these problems or doing this is you can always see if you're right or wrong. If you look at the numbers, if they match on both sides, you're right. You may not have like the lowest possible numbers, but you're right. If they match on both sides, you're right. It's balanced. Okay. Try one. Let's see if you can balance this one. P4 which is red phosphorus plus oxygen combusts to make P4O10.
The oxygen.
Right. Yep. So keep working on that one. If you've done that one, here comes another one. I'm just gonna leave off the states here for make it a little quicker. Try to bring all three of these into balance if you can. Does anybody get stuck on the second one? Well, let's do that one together because it's a common thing that comes up. We just have to know how to correct for it. So we go through and start balancing. 4 carbon on the left, 1 on the right. So we can put a 4 here so that those balance. That also changes the oxygen. So we now have 9. Then we see 10 hydrogen on the left, 2 on the right. So we're going to put a 5 here because 5 times 2 is 10. That brings 10 on both sides. That also changes the oxygen. So now we've got 8 plus 5, which is 13. And then we go to balance the oxygen. And what's the problem? Yeah, because there's 13 on the left, but you can only change, or there's 13 on the right, but we can only change the left in terms of 2, in multiples of 2, because it's O2. So if we put like a 6 there, we get 12 oxygen on the left. But if we put a 7 there, we get 14 oxygen on the left. There's no way to get 13 because we can't put a half in there. So what do you do? Yeah, if we see those fractions, that's just an evidence that we need bigger numbers. So if we double everything except that oxygen, it should work, because if you double an odd number, that will make that 13 turn into an even number. And then if we double everything, we don't have to go back and rebalance everything. We just have to fix the oxygen. So that means we put a 2 over here instead of a 1, an 8 here instead of a 4, and a 10 here instead of a 5. Then recalculate what you've got. So that, just to check everything, that gives you 8 carbons, 20 hydrogens. On the right, 8 carbons and 20 hydrogens. And now for oxygen, we've got 8 times 2 is 16, plus 10 is 26. So we can put a 13 here to get 13 times 2 is 26 total oxygens. So now it's balanced. And that comes up now and then when you've got like an even number, like a O2 or something on one side, and an odd number like O or O3 or something on the other side. That kind of thing will happen somewhat regularly. So if you get in that situation where it seems like you can't balance it because every time you go one more, you're now too many on one side, the solution is to double the whole thing. To solve this first one, that's just gets a 5 there. Something similar happens in the last one. I'll give you a couple minutes to try that one if you haven't yet, and then we'll look at it. All right, so this last one, same kind of thing happens. We can't just change one side, so we can't just go to 2O2 or 3O2, because then that's going to be more than the 3O on the other side. So we have to change both sides to bring them into balance, just like with those formulas when we had the 2 plus and the 3 plus. So we're going to need 3 of these and 2 of these, at least. And we may need more, depending on how everything else balances out, but that's a starting place. So that gets us to 6 and 6. That also changes the S over here to 2. So then we need to put a 2 over here. So you got to think about sometimes bringing both sides into balance together. rather than just changing one side to match the other side. Like everything else, this technique always stays the same, but it really takes practice. So there's lots and lots of problems in chapter 7 where you can practice balancing different equations. There's all kinds of resources all over the internet about how to balance chemical equations if you find stuff that you like. But please make sure that you practice. It's not really enough to just know the basic technique or the idea of how to do it. Make sure you actually practice it so you've really got it. And we'll have this on the quiz next Monday, along with some of the molecule stuff, polarity, the other things that we talked about today. So if you could on your way out, just show me your score. I'll pull up Blackboard, not on the big screen, but on the small screen, and I'll record your score on your way out. Thanks.